Hey yo, it's me, Frank, the function fighter, back talking to you about using a table to graph functions. Now here's a question. What do you call a goat who knows martial arts? The Karate Kid!
First vocabulary term is an independent variable. It's a variable, often x, that represents a quantity that is being manipulated. So in this section, we're going to talk about independent variables and dependent variables. An independent variable is something that we are going to manipulate. And in this section, it's likely going to be either x or t for time. So in an equation, what happens? We usually have that equation solved for one variable. What we do is we're going to plug in a value for x. And when we plug in something for x, we then simplify this side over here and we get a value for y. And you can see that y depends on whatever we plug in for x, meaning that as we plug in different things for x, we get different values for y. So y is something called our dependent variable, whereas x, in this case, is our independent variable because we are plugging in values for x and getting values for y. Here in our table, the left column is usually going to be your independent variable, whereas the right column is usually going to be your dependent variable. In a graph, the independent variable is usually your x-axis here. Now the dependent variable, we kind of just mentioned this, the dependent variable is a variable, often y, that represents a quantity that depends on or is affected by the independent variable. So here you can see we have our equation solved for y, and what happens is we're going to plug in something for our independent variable, x, then we simplify this expression right here, and we get what y is equal to. Now, y depends on whatever we plug in for x. Therefore, y is called the dependent variable in this case. And when we have a table, it's usually the right side, the right column is going to be your dependent variable. And on a graph, the y-axis is usually going to be your dependent variable. An ordered pair. It's the coordinates of a point in the plane. So they're usually denoted by an x value and a y value. And here you can see in between two parentheses, we have a 7, -2. The 7 represents the x coordinate, whereas -2 is going to be our y coordinate. This tells you where to plot a certain point on the coordinate plane. Now, a function is going to be a relation or a rule in which each element of the domain is paired with exactly one element of the range. Now, if we look at these examples down here, the first one says the relation 8, 1, -4, 1, and -5, -6 is a function because each x coordinate is paired with only one y coordinate. Each x coordinate is paired with only one y coordinate. Now, you can see that the 8 is paired with the 1 and the -4 is also paired with the 1. That's okay, as long as you don't have one x value paired with multiple y values. Now the second one over here, the relation 7, 2, -2, 3, and 7, -6 is not a function because 7 is paired with more than one y coordinate. You see how we have 7 paired with the 2 and 7 paired with the -6? The reason why that is not a function is because we have one x value paired with multiple y values. You're allowed to have one y value paired with multiple x values, just not one x value paired with multiple y values. Now, a function rule is a relationship between input and output values. To find the function rule, we have to observe the given data carefully and find how input and output values are related to each other. So here you can see our input values for each of these equations would be x here, a here, c here, and x here. Those would be values that we plug in numbers for, our independent variables, our input values. We're going to get out our output values, our dependent variables. So that would be y, b, y, and w. Those represent our output values or our dependent variables. Now, in terms of linear and nonlinear functions, we're going to talk about this in a second, but I want you to note, looking at the function rule, a linear function, those independent variables have an exponent of 1, x to the first power, a to the first power. That's for a linear function. For nonlinear functions, you're going to have exponents that are not equal to 1 for your given independent variables. Here, our independent variable c has an exponent of 2. Here, x is actually our exponent in this case. Both of these represent nonlinear functions, meaning that their graphs would not be straight lines. These graphs would be curves, whereas the graphs of these function rules would be lines. Linear and nonlinear functions. So a linear function is a function whose graph is a non-vertical line or part of a line. On the flip side, a non-linear function is a function whose graph is not a line or part of a line. So here you can see a linear function forms a line when you graph it, whereas nonlinear functions do not form straight lines. They form V's or curves. Continuous and discrete graphs. We're going to talk about this today. A continuous graph is a graph that is unbroken, while a discrete graph is composed of distinct isolated points. So just think about it. If you were to graph a line or a curve, those are continuous graphs, whereas discrete graphs are just graphs of relations, sets of ordered pairs. And you can see they're just specific points. They're specific ordered pairs that we have graphed. They're not given function rules. If you graph a function rule, you're likely going to get a curve or a line, whereas if you graph a relation, you will get discrete graphs, which are distinct points.
Did you hear about the karate champion who joined the Marines? First time he saluted, he knocked himself out. Oh, it's example time.
Example 1 says graph each function rule. So here we have our function rule. Y equals x minus 5. You can see it's x to the first power. Therefore, we know it's going to be a linear function. What we're going to do is we're going to make a table. And it's going to be an x and y table. Some people call this a t table. In this table, we're going to use the x values. 0, 1, 2, and 3. I'm going to fill those in. And you're thinking, how do I know to pick those? I don't. I just know that this is a linear graph, which means I can honestly pick any x values. And those will give me the y values that go with those x values, so then I can plot those points and draw a line through those points. That's the whole goal here. So I picked 0, 1, 2, 3. What I'm going to do is I pick these, and now I'm going to plug them in to my given function rule for x and get the y values that go with them. So I'm going to plug in 0 for x to my function rule. So my function rule is y equals x minus 5. I plug in 0 for x, and what's 0 minus 5? That's going to be negative 5. So this negative 5, I'm going to put in the table next to the 0. Next, for x equals 1, I'm going to plug in 1 for x in my original function rule. 1 minus 5 gives me negative 4, and then negative 4, now I'm going to take and plug in the table next to 1. 2, I'm going to plug in the function rule for x. 2 minus 5 is going to give me negative 3, and now negative 3, I'm going to plug in the t table next to 2. And then x is equal to 3. I'm going to plug 3 in for x in the function rule. 3 minus 5 is going to give me negative 2, and now negative 2, I can plug in the t table next to 3. Sweet! I have completely filled out my table. The next thing would be to graph it. So let's graph it. We're going to plot each of these points. So imagine them as a set of ordered pairs, as a relation. So 0, comma, negative 5. I'm going to go over 0 on my x-axis, down negative 5 on my y-axis, put a point. 1 comma negative 4. I'm going to go over 1 on my x-axis, down negative 4 on my y-axis, put a point. 2 comma negative 3. I'm going to go over 2 on my x-axis, down negative 3, put a point. And then 3 comma negative 2. I'm going to go over 3 on my x-axis, down negative 2 on my y-axis, put a point. And now I'm going to draw a line through those points. And I have successfully graphed my function rule. A couple things I want you to note. Where does this graph cross the y-axis? It crosses the y-axis at y is equal to negative 5. We have this point, 0 comma negative 5. This negative 5 is subtracted from the end of my function rule. And that's not a coincidence. Anytime you have y equals by itself on one side, whatever number is added or subtracted at the end is where your graph should cross the y-axis. And here you can see we cross at negative 5.
If I could change, you could change, everybody could change. You try.
Okay, again, we're graphing this function rule. So how do we graph function rule? We need to make a table. Here's our table. Now, what x values do you fill in? Whatever ones you want. I'm going to pick. In this case, I'm going to go 0, 1, 2, 3. That way, I know these numbers and I know they're easy to work with. So let's go ahead and do this. I'm going to take these x values and plug them in for x in my function rule. See what y values I get. So if I take 0, plug it in for x in my original function rule, what's 3 minus 0? That's 3. So the y value that goes with 0 is 3. So I plug in 3 in my table next to 0. Now take 1, plug it in the function rule for x. So what is 3 minus 1? That's going to be 2. So now I take 2, plug it in the t table next to 1. I'm now going to take 2, plug it in for x in my original function rule. What's 3 minus 2? That's 1. So I'm going to take 1, plug it in for y next to my x value of 2. And then I have x is equal to 3. I'm going to take 3, plug it in for x. So what is 3 minus 3? That's 0. So I take 0, put it next to x is equal to 3. Boom, done. Now I have a set of ordered pairs, a relation that I can graph on this graph. So let's do it. 0, comma 3. I go over 0 on my x-axis, up 3 on my y-axis, put a point. 1, comma 2. I go over 1 on my x-axis, up 2 on my y-axis, put a point. 2, 1, I go over 2 on my x-axis, up 1 on my y-axis, put a point. And then 3, 0, I go over 3 on my x-axis, up 0 on my y-axis, put a point. And now I draw a line through those, and I've successfully graphed my function rule. And you can tell that it was going to be a linear function because we have x to the first power. Anytime you don't see an exponent, that means it's to the first power. And because it's to the first power, that's a linear function. And again, where does this graph cross the y-axis? That's at 3, and that's not by accident. Here, you can see we have a 3. And we could have rewritten this as y equals negative x plus 3 because this is positive 3. But you know, because at 0, 3, this 3 that's tacked on to our x, and at this 3y value, we have a y-intercept of 3. Example 2, doing the same thing. Let's graph this function rule. First, need a table. X values that I pick. Does not matter. I have x to the first power. So I know it's going to be a linear function. So I'm just going to pick 0, 1, 2, 3. These are easy numbers to work with. That's why I do it. So now I'm going to plug in each of these x values to my function rule for x and get the y values that go with them. So I'm going to start with 0. I plug in 0 to my function rule for x. What's 0 times a half? That's going to be 0. And 0 plus 1 is going to give me 1. So I put 1 in for y next to my x is equal to 0. For x is equal to 1, I'm going to take 1, plug it in the function rule for x. So 1 half times 1 is going to give me 1 half. And what's 1 half plus 1? If I were to write this as 1 over 1, I multiply the numerator and denominator by 2 so that I can add these together. And I end up getting 3 over 2, or 1.5. So I'm going to put that in for y next to x is equal to 1. Next, when I plug in 2 for x in my original function rule, 2 times 1 half is going to be the same thing as 1 half times 2 over 1. So I multiply the numerators together and denominators together. I end up getting 2 over 2, which is going to be 1. Now what's 1 plus 1? That is 2. So I then take that 2, plug it in for this open spot next to 2 in my t-table. And then next, for x is equal to 3, I take this 3, plug it in for x in my original function rule. What's 3 times a half? Well, remember 3 is the same thing as 3 over 1. So I multiply the numerators together, denominators together, I get 3 over 2. And then I have to add that to 1. Now I rewrite 1 as 2 over 2. That way I can actually add these together. And I end up getting 5 halves, or 2.5. So 2.5. I then plug in for my t-table right here next to 3. So I can graph these ordered pairs now. 0, 1. I go over 0 on my x-axis, up 1 on my y-axis, put a point. 1, 1.5. I go over 1 on my x-axis, up 1.5, put a point. 2, 2. I go over 2 on my x-axis, up 2 on my y-axis, put a point. And then 3, 2.5. I go over 3 on my x-axis, up 2.5, and I put a point. Now I draw a line through those, and I see that, yes, I do have a linear function, and that makes sense because I have x to the first power. Also note that my y-intercept, where my graph crosses the y-axis, is at 1, and that's not a mistake. In my table, I have 0, 1. That's the y-intercept. In this function, this 1 is added to the end of my function rule. Anytime you have y by itself is equal to something times x, whatever's added to the end and doesn't have an x on it is your y-intercept. And here, you can see, checks out.
The champ is here! The champ is here! You try!
Okay, again, function rule. Need a table. Let's make a table. I have x to the first power. That means it's going to be a linear function. So I'm going to plug in 0, 1, 2, 3. You could have picked whatever x values you want. You still would have got a straight line. So now, let's go ahead and plug in these x values for x in my function rule. So if I plug in 0, what's 0 times 3? 0. What's 0 minus 6? Negative 6. So I put negative 6 next to 0. I'm going to plug in 1 for x and see what y value I get. So if I plug in 1 to the original function for x, what's 3 times 1? That's 3. What's 3 minus 6? That's negative 3. So the y value that goes with x is equal to 1 is negative 3, so I put that there. What's the y value that goes with x equal to 2? Well, I take 2, plug it in the original function for x. What's 2 times 3? That's 6. And what's 6 minus 6? That is 0. So I take 0, plug it in for this open spot next to 2. And then x is equal to 3. I take 3, plug it in my original function rule for x. Simplify what's 3 times 3, that's 9. And what's 9 minus 6, that's 3. So I'm going to take 3, plug it in for y next to this x is equal to 3. Now I plot each of these points. 0, negative 6. I go over 0 on my x-axis, down negative 6 on my y-axis, put a point. 1, negative 3. I go over 1 on my x-axis, down negative 3 on my y-axis, put a point. 2, 0. I go over 2 on my x-axis, down 0 on my y-axis, put a point. And then 3, 3. I go over 3 on my x-axis, up 3 on my y-axis, put a point. And I can draw a line through these because it's a linear function. That checks out. Also notes, what's the y-intercept? You see it's negative 6. It's also in our table, 0, negative 6. That's our y-intercept. Here, you can see because it's y equals by itself, whatever number is tacked on the end, that's going to be your y-intercept. Just like you see here, that's where it crosses. Example 3, doing the same thing, except this time it is not a linear function. You see how it's x to the second power now? That means it's no longer going to be a straight line. It's going to be a curve. So let's go ahead and do this. We're going to make a table. Last time we picked x values 0, 1, 2, 3. What I'm going to do this time, I need you to make 5 spots. And what we're going to do is we're going to put 0 in the middle and then pick 2 numbers above it and below it. So we have 0 and then -1, -2, and then +1 and +2. Now, the reason we pick these numbers we'll get into in later lessons, but for this lesson, anytime you see a nonlinear function, I need you to make a table that looks something like this. What we're going to do now is we're going to do the exact same thing we were doing. We're going to take these values and plug them in for x in our original function rule. So I'm going to take -2 and plug it in for x in our original function rule. So if I plug it in, I square it first, then I multiply it by -1. Remember, because you do exponents before you multiply, and this is basically multiplying by -1. So it becomes -4 plus 2 gives me -2. So I plug that in next to -2. What's the y value that goes with x is equal to -1? Well, I take -1, plug it in for x in my original function rule. What's -1 squared? That's 1. Then I tack on the negative. It becomes -1 plus 2 gives me +1. So I plug that in here. What's the y value that goes with x is equal to 0? I take 0, plug it in for x. 0 squared is 0 times -1 is 0 plus 2 is 2. So I take 2, plug it in here. What's the y value that goes with x is equal to 1? I take 1, plug it back in my original function rule for x. What's 1 squared? That's 1 times -1 gives you -1 plus 2 gives you +1. So I take that, plug it in here. And then what's the y value that goes with x is equal to 2? I take 2, plug it in my original function rule for x. 2 squared gives me 4, and then 4 times this -1 that's out front is -4 plus 2 gives me -2. So I plug that in here. Now you plot the points just like we usually do. So let's plot each of these points. -2, comma -2, I go over -2 on my x-axis, down -2 on my y-axis, put a point. -1, comma 1, I go over -1 on my x-axis, up 1 on my y-axis, put a point. 0, comma 2, I go over 0 on my x-axis, up 2 on my y-axis, put a point. 1, comma 1, I go over 1 on my x-axis, up 1 on my y-axis, put a point. And then 2, comma -2, I go over 2 on my x-axis, down -2 on my y-axis, put a point. So now what I do is I draw a curve that goes through these points, and it's going to look something like that. This is called a parabola, and we'll get into that later on. Now that you've graphed it, again, notice, even with a curve, as long as you have y equals by itself, this 0, 2 is still going to be your y-intercept, because it intercepts the y-axis at 2, and it's still just this number that is tacked on the end. Just want you to notice this pattern.
What's a boxer's favorite office supply? A 3-hole punch! You try.
Okay, doing the same thing. Here, again, we see x is to the second power, meaning we're going to get a curve again, and it's going to be a parabola, just like we had before, because it's to the second power. So we make a table where we put 0 in the middle and pick 2 numbers above and 2 numbers below. And we'll get into that later on, why we're doing that and why we're picking numbers like this. But for right now, just make a table that looks like this anytime you have x to an exponent besides 1. So now, let's go ahead and plug these in for x in our original function and see the y values that go with them. So what y value goes with -2? I'm going to take -2, plug it in for x in my original function. What's -2 squared? That's 4. And what's 4 times 2? That's 8. So I plug that in here. What's the y value that goes with -1? I take x is equal to -1 and plug it in for x in my original function. What's -1 squared? That's +1, and 1 times 2 gives you 2, so that goes here. What's the y value that goes with 0? So I take 0, plug it in for x in my original function. What's 0 squared? That's 0 times 2 is 0 still, so I plug that in here. What's the y value that goes with 1? I take 1, plug it in for x in my original function. 1 squared is 1. 2 times 1 is 2, so I plug that in here. And then last but not least, 2. I'm going to take 2, plug it in for x in my original function. 2 squared gives you 4. 4 times 2 is 8, so I plug that in here. Now I have my set of ordered pairs that I can graph. -2, comma 8, I go over -2 on my x-axis, up 8 on my y-axis, put a point. -1, comma 2, I go over -1 on my x-axis, up 2 on my y-axis, put a point. 0, comma 0, that's the origin, so I put a point right at the origin. 1, comma 2, I go over 1 on my x-axis, up 2 on my y-axis, put a point. 2, comma 8, I go over 2 on my x-axis, up 8 on my y-axis, put a point. Then I draw a line, in this case a curve, going through these points. That gives me this parabola. Again, we'll talk about that later on. And I have successfully graphed my function rule. Again, notice, what is the y-intercept? It's 0. And that is because in our table we have 0, comma, whatever our y-intercept is. That's 0 in this case. And here, do we have anything added or subtracted at the end? No, that's why it's 0. In our graph, you see, it is 0. That's our y-intercept. That's where the graph crosses the y-axis. Now our word problem says the cost C in dollars for delivered pizza depends on the number P of pizzas ordered. This situation is represented by the function rule C is equal to 5 plus 9P. Graph the given function rule and tell whether the graph is continuous or discrete. Remember, step 1, we're not scared. So step 2, what does it want? It wants us to graph the given function rule and tell whether the graph is continuous or discrete. Okay, so we're just going to graph this function rule. So what is our independent variable? What's our dependent variable? Well, you can see here that we're solved for our dependent variable because C depends on whatever we plug in for P. That means P is our independent variable. And notice, P is raised to the first power. Because our independent variable is raised to the first power, this is going to be a linear graph. So I'm going to make my table, and my independent variable is P, my dependent variable is C, so we make it like this, where P is in the left column, C is in the right column. And now, what am I going to plug in for P? Well, since it's linear, let's just plug in 0, 1, 2, and 3. Sweet! Now all I have to do is take these P values, plug them in the original function rule for P, and get the C values that go with them. So let's go ahead and do that. P equals 0. We're going to take 0, plug it in for P in our function rule up here. What's 9 times 0? Because we have to multiply before we add. Got to do PEMDAS. So 9 times 0 is 0. 5 plus 0 gives you 5. So I'm going to take 5, plug it in next to 0. What's the C value that goes with 1? I'm going to take 1, plug it in for P in my original function rule. What's 9 times 1? I get 9. And then 9 plus 5 gives you 14. Plug that in next to 1. What's the C value that goes with 2? So I take 2, plug it in for P in my original function rule. 9 times 2 is going to give you 18. What's 18 plus 5? That's going to be 23. So I plug in 23 here. Last but not least, what's the C value that goes with 3? So I'm going to take 3, plug it in for P in my original function rule. 9 times 3 gives you 27, plus 5 is going to give you 32. Now I'm going to take that 32, plug it in this last open spot here. Now I have a set of ordered pairs, a relation that I can graph. Here's my graph. Let's go ahead and label the axes. So this x-axis is going to represent your independent variable, which in this case is P. So this will be the number of pizzas. Whereas the y-axis represents your dependent variable, so that would be cost. And now since we have numbers that are above 10, we're going to make this cost in tens of dollars. So 1 represents 10, 2 represents 20, 3 represents 30, and so on. So now we can fit all of these points on this graph. Let's do it. 0, 5. We go over 0 on our x-axis, up 5 on our y-axis, which would be here, and we put a point. 1, 14. We go over 1 on our x-axis, or p-axis, up 14 on our y-axis, or c-axis, and put a point. 2, 23. We go over 2 on our x-axis, or p-axis, up 23 on our y-axis, or c-axis, put a point. And then 3, 32, over 3 on our p-axis, up 32, which would be about right here. On our c-axis, put a point. And you can see, yes, this is a linear function, but should we draw a line through it? That is the question. And the answer is no. This must be a discrete graph. Because you can't order fractions of a pizza, you can't say, yeah, give me 1/3 of a pizza. That doesn't work like that. Okay, you either order a small, medium, or large, and each time it's 1 small, 1 medium, 1 large. So because of that, this must be a discrete graph.